All right, let's consider equilibrium shifts. And more specifically, what we're going to do now is we're going to try to apply the kinetic perspective and the thermodynamic perspective to explain the equilibrium shift. To begin with, let's take a generic reaction. Weak acid HA reacting with water to produce H3O plus AQ plus the conjugate base, which is A minus AQ. Now, let's consider the case where we add A minus to the system. Adding A minus AQ to the system, okay? Adding A minus AQ, the first thing it would do is it would increase the A minus concentration. So A minus concentration would increase, okay? And as a result of that, we can think about this perturbation in two ways, the kinetic or thermodynamic. So let's think about the kinetic argument over here. So the kinetic argument is all about the rate forward, which is the forward rate constant times the weak acid concentration. And then with respect to the reverse rate, we call this R sub R, which is the reverse rate constant. And for that, we have H3O plus concentration and A minus concentration. Now, what we have done here is, let me pick a different color if I can, okay? Due to this perturbation, okay, at the equilibrium, the forward rate must be equal to the reverse rate. That's the definition of the equilibrium. But because of the perturbation, because of adding A minus, okay, the A minus concentration increases. And as a result of that, the reverse rate increases, okay? And therefore, what we have is, we see that the reverse rate must be greater than the forward rate due to this perturbation. Now, if the reverse rate is greater than the forward rate, that means the products in this reaction, which is these guys over here, must be converted to reactants. If I can erase that, see. Okay, so therefore, more I can't draw that for some reason. Give me a second. Okay, therefore, more reactants must be formed until the reverse rate becomes equal to the forward rate again. Okay, and we say that now the equilibrium has shifted towards the reactants. Therefore, the equilibrium shifts towards reactants. Okay, so that is how we can explain the equilibrium shift due to this perturbation. Okay, and then now, because the equilibrium is shifting towards the reactants, that means our products are consumed. Our products over here are consumed to produce more reactants. Okay, as a result of that, our H3O plus concentration goes down. Okay, when the H3O plus, let me write that down. H3O plus concentration goes down. As a result of that, the pH increases. Okay, and that's the effect. That's the effect on the pH due to this perturbation. Okay. Now this is called the kinetic. Let me see. Okay, this is called the kinetic perspective. Okay, we can explain the same thing using the thermodynamic perspective. Let's talk about the thermodynamic perspective on the other side. Okay, so when it comes to thermodynamic argument or thermodynamic perspective, it's all about the reaction quotient. Okay, reaction quotient is the product concentrations over reaction concentrations. Okay, we have H3O plus concentration times A minus concentration divided by HA concentration at any given point is called the reaction quotient. Now, at the equilibrium, the reaction quotient is equal to the equilibrium constant. Okay, but what happens is we are perturbing the system. Okay, due to this perturbation, we are increasing the A minus concentration, and as a result of that, the numerator increases more than numerator is going to be greater than the denominator. Therefore, the Q becomes greater than K. Okay, so whenever Q becomes greater than K, okay, you need to produce more reactants until Q becomes equal to K again. Okay, let me do that graphically as well. Okay, this is what we have. This is our Q, and this is our time, and then this is our K value. Now at the beginning, everything is at K. I mean, at the equilibrium, everything is at K. Okay. Now, due to the perturbation, because we added A minus, the Q increases compared to K value. Okay. So that's going to be our perturbation. Now the Q is over here. Now, what needs to happen is Q needs to get back down to K with time. And for it to get back down to K value, it needs to produce more reactants. Okay, therefore the equilibrium shifts towards reactants. Let me write that down. Okay, more reactants must be formed until Q becomes equal to K again. Okay, therefore equilibrium shifts to reactants. Okay, and that's how we explain the shift of the equilibrium due to this perturbation using thermodynamic perspective. And also, I mean, similarly to the kinetic argument, okay, we know that for when Q decreases to become equal to K again, you need to be consuming the products. You're consuming these guys to produce more reactants, and as a result of that, the H3O plus concentration goes down. Okay, H3O plus is consumed, therefore H3O plus concentration goes down, therefore pH goes up. Okay, and that's how we can explain the equilibrium shifts using kinetic argument and thermodynamic argument. All right, let's see. All right, let's do another one. Let's take the same equilibrium. Okay, let's take this weak acid. Okay, HAAQ reacting with H2O. Okay, producing H3O plus and Q minus. Right. this time what we're going to do is we are going to add more water. Okay, let's say that the perturbation is adding water. Add H2O liquid. Okay. Now, adding H2O liquid will not increase the concentration of H2O. Okay, the reason is H2O is already is in the liquid phase. Okay, adding a liquid to another, adding a liquid does not change its concentration because the liquid concentration does not change. Okay, however, adding the liquid increases the amount of water where these aqueous substances are dissolved at. All right, so we have HA aqueous, H3O plus aqueous, and A minus aqueous. Now, because we add water, all of these concentrations decreases in value because we are diluting them, right? And then what we want to consider is what we'll do to the equilibrium. Okay, now let's think about this perturbation first we'll think about this perturbation in the kinetic perspective. Okay, in a kinetic argument. Okay, again, kinetics is all about the forward rate, which is K forward times the shear concentration in this case, and the reverse rate, which is reverse rate constant times H3O plus concentration times A minus concentration. Okay, now what we have done here is we have added water. Adding water will decrease all the aqueous concentrations. Okay, it will decrease the concentration of HA, it will decrease the concentration of H3O plus, it will decrease the concentration of A minus. Okay, so it's going to decrease all of them. Now, however, we are decreasing two things in the reverse rate while we are only decreasing one thing by the same amount in the forward rate. And as a result of that, okay, the reverse rate decreases more compared to the forward rate. Okay, so the reverse rate goes down more compared to the forward rate. Therefore, the reverse reaction rate will be less than the forward reaction rate. Okay, since the forward reaction is greater, okay, that means the reaction must be producing more products. Okay, therefore, more products are formed until the reverse rate becomes equal to forward rate again. Okay, and this shifts the equilibrium towards the products. Okay, equilibrium is shifted towards products or to the right. Okay, and that's how we understand the shift using the kinetic argument when we add water. Okay, now the other issue is, even though we are shifting the equilibrium towards the products, okay, it should produce more H3O plus. That is true, but however, due to the perturbation, okay, because we added water initially, it diluted our H3O plus concentration. Okay, and then this dilution of H3O plus concentration due to the perturbation is much greater than what is compensated by this equilibrium shift. Okay, so the perturbation is always greater than the shift. Okay, so overall, H3O plus concentration has gone down, and as a result of that, pH should increase. Okay, so the thing to remember is perturbation is always greater than the than the shift. Okay, so let me even write this down. Perturbation is greater than the shift. Okay, this is true for both kinetic and thermodynamic arguments. All right, just to complete our notes, let's do the same thing. Same thing with the thermodynamic argument as well. All right, so this is our kinetic argument. If you go to the thermodynamic argument, see, thermodynamic argument. Okay, so the thermodynamic argument is all about the reaction quotient, which is the products over reactants. Okay, now due to adding water, when we add water, the perturbation is we decrease the concentration of all the aqueous species. Okay, that means we are decreasing H3O plus, A minus, and HA. Okay, now because we are decreasing two things in the numerator, okay, we are decreasing the numerator more than the denominator, and as a result of that, the Q is going to become less than the K value. Okay, if we draw a graph to represent this, okay, at the equilibrium Q, everything is at K. At the equilibrium, everything is at K. Okay, due to the perturbation, the Q decreases. Okay, and this Q should increase with time so that it can come back up to K value. So it should look something like that. Okay, and for Q to increase, we should produce more products. Okay, therefore we can write that. Therefore, I need blue. Okay, therefore, more products must be formed until Q is equal to K again. Okay, and this shifts the equilibrium. Okay, now for the equilibrium shifts towards products. Yeah, shifts to products. Okay, but then again, the perturbation is greater than the shift, even though more H3O plus should be formed due to the because of the shift. Okay, the decrease of the initial decrease of the H3O plus concentration is much greater. Now, for overall, H3O plus concentration has decreased. Therefore, pH must increase. All right, I think that's all I want to cover today. I'll see you guys soon in class. Bye, everybody. I'll do this.